Right, let's talk about enthalpy and stoichiometry. So we're going to use our example previously. We're going to burn our propane, C3H8 plus 5O2 goes to 3CO2 plus 4H2O. And the delta H here is equal to negative 2044 kilojoules. And so this value here, this negative 2044 kilojoules, it's per mole of reaction. Per mole of reaction. So let's see what kind of equalities we can write, our conversion factors we can write between our chemical reaction and our delta H for the reaction. So what this tells us is that 1 mole of propane can be burned to release 2044 kilojoules of energy. The reason that it's 1 mole is because we have a 1 in front of here. Conversely, we could write it in terms of the oxygen. So we could write 5O2. 5 moles of O2 is equal to negative 244 kilojoules, right? Or we could write 3 moles of carbon dioxide or we could write 4 moles of water. And again, because we're writing these as equalities, they're not true equalities. They are only true for this specific reaction. So let's see how we're going to use that. So we're going to say a tank of propane contains 11.8 kilograms of propane. How much heat is released when it is all burned? Right, so let's take a look at what we've got. One value that we've got in our equation here, or in our problem here, is that we have 11.8 kilograms of C3H8. So 11.8 kilograms of C3H8. And anytime we have mass, we want to go to moles, but what we notice here is we have kilograms, not grams. So the first thing we have to do is switch over to grams. So 1 kilogram down on the bottom is equal to 1,000 grams up top. Cancel that out, cancel that out. And now we're at grams. Pretty much anytime that we're at grams, we want to go to moles. To go to grams to moles, we have to calculate the molar mass. So we have the molar mass of C3H8. It's going to be equal to the mass of 3 carbons, which are each 12.011 by themselves, plus the mass of 8 hydrogens, which are each 1.008 themselves. Sum those up, you get 44.097 grams per mole. Plug that into here. Since we have grams up top here, grams is going to go down on the bottom. Grams and grams cancel out. And so now you can see the units that we're left with are moles of CH or C3H8. And what we want to get to is our heat, right? How much heat is released. So we want to know how many kilojoules. So if we take a look back at our equalities, we want to find where we compare moles of C3H8 and heat, right? And that's this equality right here. So in this case, it's just 1 mole of C3H8. Notice that both C3H8 and moles are on the top. So we want to put moles of C3H8 down on the bottom. So 1 mole C3H8. And then moles and moles cancel out, and C3H8 and C3H8 cancel out. And on top, we're going to have negative 2044 kilojoules. Go ahead, plug through the math. You should get something like negative 5.46957 kilojoules. Then we think about our significant figures. In this case, this value right here has only 3 sig figs. So our answer should only have 3 sig figs. So this 6 is our uncertain digit. And so that there's a 9 next to it. So that's going to round up. So negative 4 or 547. And then just change the rest to zeros, 0, 0, 0 kilojoules. So 547,000 kilojoules of energy are released when you completely burn through a propane tank. course, is a pretty large number. You can write in scientific notation as well. So you could write it as negative 5.47 times 10 to the 5 kilojoules, right? And then there you can plainly see that we only have 3 sig figs. And of course, our value here is negative, which just tells us that heat is released, which is exactly what we'd expect for burning propane. And as always, the key here is practice.